Okay, so what did we discuss in the section 5? In the section 5, we actually solve one problem. Let's do it step by step. First, we define a sequence of elementary factor. Remember that this is a definition 5.10. Okay, well, we have elementary factor. Elementary factor says E0 of Z is 1 minus Z, and EP of Z is 1 minus Z times exponential of Z plus Z squared over 2 up to Z to P over P if P is greater than or equal to 1. Okay, so we have those elementary factors, so-called. This was introduced by Weierstrass. Okay, and then the 5.14, the Weierstrass factorization theorem. Factorization theorem tells us for the entire function, f is entire, and we have an sequence of non-zero element with multiplicity no, let's so repeat it according to multiplicity. Okay, so if you don't want to repeat it elements, then you determine, you write the multiplicity sequence. If you allow repeated element, then you don't need a multiplicity sequence. And this sequence is the sequence of zeros. Of f. Okay, this is the sequence of zeros f. And then the conclusion, this is a assumption, then the conclusion, then there is another entire function g of z such that f of z is equal to z to mth power. Here it represents the 0, and exponential of g of z and the infinite product and from 1 to infinity EP sub n of z over a sub n. Here EP is determined by the function f. Okay, so this is a factorization, Weierstrass factorization theorem. So exponential g of z does not contribute to 0. This gives you the 0, 0. This gives you the 0 a sub n. Okay, so that's a factorization. This theorem works for the entire function. If the function is not entire, the generalization will be the next theorem, 5.15. Okay, so the 5.15 says we can actually construct functions based on the given zeros. We can construct, so G is the region, and AN is a sequence in G with no limit point. Of course, if it has no limit point, this a sub n, oh, okay, and distinct. Let's just assume it is a distinct sequence with no limit point and a distinct. There's no repeated element. Because here we do not allow repeated element. Mn is a sequence of natural numbers. Sequence of natural numbers. Then there is an analytic function f over g with zeros exactly a sub n and the multiplicity m sub n. Okay, so this analytic function has exactly zeros a sub n with exact multiplicity. So we can design analytic functions. We can design the analytic function. And the proof of theorem 515 is long. You have to consider the special case, and you're going to show that this special case is sufficient for the general case by a Mobius transformation. Right? So this is the main theorem or main result of the section 5. This is an abstract discussion. And the next section, section 6, we're going to apply this main theory to some example. We're going to see what is the real factorization of certain functions. Okay, so we want to find application. We want to really decompose or factor some functions. Factorization of the sine function. Factorization of a sine function. Okay, sine function is the entire function. Okay, sine function is in the complex analysis, sine function is defined by the exponential function, so it's an entire function. So, in order to avoid pi, we do not study sine z. We study sine pi of z. We just want a nice zeros. So sine pi of z is exponential of I pi of z minus exponential of negative I pi of z divided by 2i. Okay, and we can see that sine function sine pi of z has zeros exactly integers, positive, negative, and 0, exactly integers, and all zeros are simple. All zeros are simple. There's no repeated zeros. Okay, there's no repeated zeros. Okay, so that's a result we can easily derive from this from this expression, you just set it equal to 0 and the numerator is 0, exponential function, it becomes exponential 2 pi I z is equal to 0, then z can only be integers. That's all. It's not difficult. It's not difficult. And in the factorization theorem, we need a sequence of a p sub n. P sub n is determined by what? By the theorem 5.12. P sub n is used to make this infinite product convergent. Okay, so P sub n has a condition. P sub n has a condition. First, that it's in the theorem 5.12. So we need the limit of all zeros approach infinity if we label them 1, 2, 3, 4. Okay, and they repeated the finite many times. And P sub n satisfy the property sigma r over ops value of a sub n to p plus 1's power n from 1 to infinity. We need this less than infinity. We need a convergence for all convergent sequence, for all r, for all positive r. Then the infinite product convergent. Okay, so this is theorem 5.12. Okay, so now we have a sub n equal to n. A sub n. Well, let's not say a sub n is equal to n. A sub n becomes 0, 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4. That's all. Let's do this way. Okay, and this one, remember this is 1 over n squared. We know this one converges, right? This one converges. So it's a p sub n plus 1. We also want p sub n as small as possible because of p sub n, if p sub n is very big, then your elementary factor will be more complex. We want p as small as possible, and also p satisfy this condition. So naturally, so we can see that p sub n can be just a 1. When p sub n is 1, plus 1 is 2, so you will have a denominator n squared. You will have denominator n squared, right? Okay, so we get p sub n equal to 1, exactly 1. Then what do we have? We have the sine pi z is equal to exponential g over z. Remember the 0, where's 0? Yes, all the integers, exactly integers. Zeros. This a sub n, we exclude 0. A sub n, we exclude 0. We don't allow 0 in this sequence of zeros. So 0 is separately discussed. So it's a simple 0. So it's just z to 1, and infinite product of what? Infinite product of you see, it's n from 1 to infinity, 1 minus z, 1 minus z over n, not z over n. We always, where is it? Yeah, okay, so z over a sub n, and exponential of what? Exponential of this z sub n. Exponential z sub n. And also in infinite product, and from -1 to -infinity, 1 minus z over n exponential z over n. The same thing, same formula, but have different infinite product. The limit from positive infinity, positive 1 to positive infinity, -1 to negative infinity. And you combine these two. These two, they can be combined because one is positive, one is negative. You get the difference of squares. And these two, they're cancelled. Exponential z2, z over 1, exponential z over -1, they cancelled. So these two things are cancelled. So you only have you only have 1 minus z squared over n squared, infinite product n from 1 to infinity. Okay, so even though they have the same formula, but one has negative sign, the other one has a positive sign, they are always cancelled. All right, so the sine pi z is almost determined. It looks like this, except the function, entire function g of z, except the entire function g of z. So we're going to determine g of z. So we need to determine g of z. Well, let's see. That this becomes a tricky part. We have to use the derivative. So f prime, fx, fz as sine pi z. Then f prime of z is pi cosine pi z. Okay, so f prime of z over f becomes pi cotangent of pi z. And the other way, f prime is what? F prime, you are going to apply the product. You will get g prime of z exponential g over z, z product, and from 1 to infinity, 1 minus z squared over n squared. This is one term. And plus you differentiate the middle term, exponential g over z, infinite product, and from 1 to infinity, 1 minus z squared over n squared, and plus, it's long, plus you're going to differentiate this. You're going to differentiate this. Differentiate this, well, how do we write it? The exponential g over z, z, well, let's see, we have infinite product n from 1 to infinity, n is not equal to m, 1 minus z over n squared. And when you have m, you will get a negative m squared to z, sigma m from 1 to infinity. Okay, so that's how I write it. So first you pick up an element, the element m, and you're going to differentiate that m's term. When you differentiate m's term, it does not appear in the infinite product. Every time you differentiate one, m is from 1 to infinity. For m's term, you apply the power rule. Okay, so add this. It's very long. So fz over f this first term, the first term over this expression, you will see that this first term over the expression, you will just get g prime of z. And second term over f, you get 1 over z. And third term over f, third term over f, what it is? It's going to be, okay, this one cancelled, this one cancelled. You will have sigma, and each time you will have 1 minus z over z square over m square, and times 2 negative 2z m square. M is from 1 to infinity. Okay, so when m is 1, you differentiate first term, you have this one, but the first term still appears in this product, so you keep the first term, and then you get the second, third, and the infinity, and so on. Right? So let's this is on the numerator, so we multiply m squared for both sides, for top and bottom, not both sides. Looks like this, and then we switch m squared and z squared. We don't want this negative sign, so we get in the book they use the letter n instead of m. Have this. All right, have this. Okay, so this is exactly f prime of z over f of z, and f prime of z over f of z is also equal to pi cotangent of pi of z. Okay. Okay, so now we need to go back to, okay, let me see. In the textbook, they say we'll have exercise V point, chapter V, section 2, problem 8. Okay, this one is on page 122. On page 122, they use the integral, counter integral. They get that the pi cotangent pi of z, or pi of a, in the book is pi of a. It is equal to 1 over a plus sigma 2a over a squared minus n squared, and from 1 to infinity. So you see here, we don't, just simply compute it. We actually have to integrate all the information we have. Okay, so by this exercise, we have this formula. If you replace a by z, you will have that actually this whole thing should be equal to pi cotangent of pi z. The g prime of z has to be 0. Hence, g prime of z is 0, and g of z is a constant a. A constant number. Okay, so we must have g of z as a constant. G of z as a constant. Let's see what we have. We have sine pi z is equal to exponential. This time it's a constant, and z infinite product, n from 1 to infinity, 1 minus z squared over n squared. All right. Well, they want some symmetric form, so we divide both by pi times z. So we get a sine pi z over pi z equal to what? Equal to the exponential of a over pi. Here, this infinite product n from 1 to infinity 1 minus z squared over n squared okay, and okay, so this is the formula, and then remember that for whatever thing this stuff is equal to 1. This stuff is equal to 1. So when z approaches 0, this term becomes 1. So it is equal to EA pi. So e to a over pi is equal to 1. So e to a is equal to pi. Okay? E to a is a pi, then what we have? Hence, sine pi z is pi z infinite product n from 1 to infinity 1 minus z squared over n squared, z squared over n squared. Okay, this is a convergent infinite product which is also uniform over arbitrary compact subset. So we get this factorization. This is not a trivial result. Even we assume, we take for granted that this, where is it? Here. Even we take it for granted that this, the Weierstrass factorization, still we need this important exercise. I don't think we did this exercise when we studied that chapter, but you will see that many things are related among this within this factorization. It's a very important and difficult exercise, frankly speaking. All right, so this is the section. What is the section? Okay, section 6, the factorization of the sine function. The factorization of the sine function. So next, we are going to study another section, the section about the gamma function. Let's separate it. We're going to discuss in the different chapter, different video. That's totally different. It will take a long time. Okay, we finish this video and we will continue in another video. Thank you.